In discussing Java classes, we have previously created methods and utilized them in various ways, depending on the specific purpose of the tutorial and the example they were used in. The methods we have covered up to this point have not been extremely complex ones, consisting of somewhere around 10 to 15 lines of code at the most. In this video, we will discuss method decomposition, which consists of breaking down one method into multiple methods, something that is recommended not only when one method becomes too large, but also when it makes sense to break down a complex task into one or more tasks, with each task having its own purpose contributing to the larger task at hand. To explain this, let's look at this card guessing game. The way it works is the computer will pick one card from a regular deck of 52 cards. After the computer picks a card, the user will continue to guess which card the computer picked until the user picks the correct card. To begin, all logic to create this game will be contained within the main method, somewhere around 100 lines of code. Now, this is not the biggest program ever, however, you can see that having 100 lines of code in one method is not very eye-friendly. And for this specific method here, there are multiple tasks being done to where it makes programmatic sense to decompose this one method into multiple methods. So let's go ahead and do that. But first, let's run the program so you can get an idea of exactly how the game works. Then I'll go through the code line by line to explain how it works before method decomposition is performed to make this program more elegant. So if we run the program, we are prompted, computer has picked a card. Guess what card the computer picked? First, we will need to pick a face value, which will be either 2 through 10, a J for a jack, a Q for a queen, a K for a king, or an A for ace. Let's go ahead and choose a king by inputting a K. Next, we will need to pick a suit. I'll input diamond. If the computer did pick a king of diamonds, we will be prompted, you guessed the right card, you win. But if the computer did not pick a king of diamonds, we will be prompted, that is not the card the computer picked, try again. And the program will continue to accept user input until the correct card is picked. Now obviously this is not the best game ever made, as it can take up to 52 tries in order to win the game. But we're going to overlook that, as the purpose of this tutorial is not to make the best game ever, but to instead explain method decomposition. So since we have a good understanding of how the game is played, let's review the code to see how it is programmed to work. Looking at the first line of code in the main method, the random class is being used in order to generate a random number, which will be used to select a card for the computer. We store the random number in an int variable called computer card by using the nextInt method of the random class. And since a deck of cards contains 52 individual cards, we limit the possible random numbers to 0 through 51 by using 52 as a parameter in the nextInt method. Next, two string variables are initialized. One is called suit and the other is called face value. As you may have guessed, the string variable suit will be used to store the suit of the computer's card, and the string variable face value will be used to store the face value of the computer's card. Next comes a few if statements that are used to determine the suit of the card assigned to the computer. If you're unaware, a deck of cards has 4 suits: spades, hearts, clubs, and diamonds. Each suit has an equal amount of cards associated with it. So if we take the total number of cards in a deck, 52, and divide it by the number of suits in a deck, 4, we get 13. Therefore, there are 13 spades, 13 hearts, 13 clubs, and 13 diamonds in a deck of cards. So, to process that programmatically, if the random number assigned to the int variable computer card is between 0 and 12, the card will be assigned a suit of spade. If the random number assigned to the int variable computer card is between 13 and 25, the card will be assigned a suit of heart. If the random number assigned to the int variable computer card is between 26 and 38, the card will be assigned a suit of club. And if the random number assigned to the int variable computer card is between 39 and 51, the card will be assigned a suit of diamond. This covers all 52 possibilities of what the variable computer card could possibly be. For example, if the number 25 is randomly assigned to the int variable computer card, the computer's card will be a heart, since 25 falls within 13 and 25. If the number 42 is randomly assigned to the int variable computer card, the computer's card will be a diamond, since 42 falls within 39 and 51. Alright, so now that the suit is covered, the next section assigns a face value to the computer's card. This task is a little trickier to grasp, but not at all overwhelmingly difficult to understand. Once again, the 52 possibilities are broken up into 4 groups, each having 13 possibilities. The numbers used in the group are the same as before, with the first group being numbers 0 through 12, the second group being numbers 13 through 25, the third group being numbers 26 through 38, and the last group being numbers 39 through 51. Looking at the first group of possibilities, 0 through 12, We can see that a switch statement is used to assign a face value of J if the computer's card has a value of 9, Q if the computer's card has a value of 10, K if the computer's card has a value of 11, and A if the computer's card has a value of 12. So what if the computer's card is 0, 1, 2, 3, 4, 5, 6, 7, or 8? In these cases, we will add 2 to the number assigned to the int variable computer card and assign that value to the face value of the computer's card. We add 2 because a deck of cards does not contain any zeros or ones. Instead, the face value of a card can be either a 2 through 10, a J, a Q, a K, or an A. So because of that, if for instance 0, the lowest value in this section, is assigned to the variable computer card, by adding 2 to 0, we assign the lowest possible face value in a deck of cards to the computer's card, that face value being 2. If the random number assigned to the int variable computer card is 3, the fourth lowest value in this section, by adding 2 to 3, we assign the fourth lowest face value in a deck of cards to the computer's card, that being 5. This same method is used to assign a face value to the computer's card for all other groups of possible random numbers that can be assigned to the int variable computer card. The only thing that changes is the values used in these switch statements in order to adjust to that specific group of 13 possible numbers, as well as a different number is subtracted from the variable computer card depending on which group the random number generated falls in order to perform in the same manner as the first group we just discussed. So for example, if the number 25 is randomly assigned, since 25 is greater than 12 but less than 26, the computer's card will be assigned a face value of ace. But say the random number is 13. This number will fall in the same group since it is greater than 12 and less than 26, but since it is not a 22, 23, 24, or 25, we will instead subtract 11 from 13, which will give us 2. Notice 13 is the lowest value this group contains, and 2 is also the lowest face value in a deck of cards. Essentially, adding 2 for this group of numbers, subtracting 11 for this group, subtracting 24 for this group, and 37 for this group, make sure the value stored in the variable face value actually represents a face value of a real deck of cards. Once again, either a 2 through 10, a J, a Q, a K, or an A. One other thing to point out here is that we are converting an integer value into a string using the value of method. You'll see why this is done shortly. Alright, so now that the computer's card has been assigned a face value and a suit, the next thing to do is to prompt the user to pick a card and then compare the user's card choice with the computer's card. To do this, a while loop is used with the condition being an int variable called flag, which is initialized to 0. The program first prompts the user to select a face value. The user's input is stored in a string variable called userCard. Next, the program prompts the user to input a suit. Here the user's input is stored in another string variable called userSuit. The program will then echo what the user selected using a print line statement. And finally, the user's choice of a card will be compared to the computer's card. This is done using a method from the string class to first compare the string variables userCard and face value. We are able to compare these as strings since we converted the int variable to a string here. If we did not perform this conversion, this action would not be possible. Okay, so after that, the string variables userSuit and suit are compared. If both the string variables userCard and face value are equal, as well as userSuit and suit are equal, the string "you guessed the right card, you win" will be printed to the console, and the variable flag will be set to 1, breaking out of the while loop and ending the program. However, if the string variables are not equal, the string "that is not the card the computer picked, try again" will be printed to the console. And since no action is performed on the variable flag, it will remain 0 and the while loop will continue to loop until the user inputs the right card. Okay, so now that we know how the program works, let's talk about method decomposition. Within this program, there are a few different tasks being performed. First, a random number is assigned to the int variable computer card. Next, a suit is assigned to the computer's card. Then, a face value is assigned to the computer's card. After that, the program enters the while loop in which first the user is prompted to input a face value, and next the user is prompted to input a suit. This leads into the user's choices being compared to the computer's card, which determines whether the program continues because the user's choices were incorrect or the program ends because the user picked the right card. Each one of these individual tasks I just described can be broken down into their own methods. In other words, we can perform method decomposition to decompose this one method that performs many tasks into multiple methods, each performing a specific task. So let's do that. In total, we're going to create 4 new methods that will each contain one main task currently being performed in the main method. The first method will be a public static method with a return type of string. This method will be called checkSuit, and it will have one int parameter that we will call num. All this code that handles the assignment of a suit to the computer's card will be cut and pasted into the new method. Instead of using computer card here, we will use num since computer card will be passed as the parameter when this method is called. A string variable named suit will be initialized within this method, and that variable will be what is returned. Now we can use this method to initialize the suit variable within the main method. So the same actions that were performed to assign a suit to the computer's card are still being used. The only difference is that the logic was moved into its own method in order to make this program more elegant. So the int variable computer card is passed as a parameter to the new checkSuit method. This value is then being used to determine what suit should be assigned to the computer's card. And that suit is then returned from the checkSuit method and assigned to the string variable suit in the main method. Practically the same process will be used to decompose the main method logic to determine the face value of the computer's card. Since this is basically the same process, I will not explain it step by step like I just did with the checkSuit method. Instead, you can just see how the logic is being isolated into a method called checkValue. Okay, now let's further decompose the main method by separating the logic to prompt the user to pick a face value into a method called getUserValue. This method will also return a string, which will be the input accepted from the user, but it will not require any parameters. The value returned from this method will be stored in the main method string variable userValue. The same process will be used to create another method called userSuit, where the code to accept user input of a suit choice will be moved. This method will return a string which will be assigned to the main method string variable userSuit. Now as you can see, method decomposition has been performed on the main method. The logic of individual tasks has been separated into the new methods in order to add clarity to the actions performed in this program. If we run this program, we can see it performs in the same manner with the main method containing roughly 30% of the lines of code it originally did. If we wanted to, we can clean this up even more by separating the added methods into their own classes. We can store these two methods in a class called cardConversion, and we could store these other two methods in a class called userChoice. We only need to add class names in the invocations of these methods, and once again the program performs just as it should. Overall, method decomposition adds elegance to code. It may be safe to say there is no such thing as overkill when it comes to method decomposition. In decomposing methods, the closer you can break them down to somewhat of an atomic level, the better.